Welcome to the pre-recording of lecture 18 of MCS 481, an introduction to computational geometry. We are in the middle of the book, but I will try to make this self-contained as possible. So today we consider a randomized incremental algorithm to solve the point location problem in the plane. What's that problem? Well, you have a map, you have a position. Can you locate yourself given that position on the map? Um, that's something that you needed to do with a paper map, but in the current age of smartphones, uh, algorithms can do this extremely quickly. So the purpose of this lecture is kind of indicating that with trapezoidal maps and a directed acyclic graph, we can solve this problem quite efficiently, provided the input is the way the maps were constructed. The maps were constructed in a randomized order on randomized inputs to avoid very bad unbalanced search trees. Okay, here is the problem again. We introduced this in the last lecture. So you have a map, you have a location, you have coordinates. Do you actually know, can you situate yourself on the map given these coordinates? So here is an example. Geometrically, we have a subdivision of the plane. We have line segments, so you can think of them as roads. We have vertices, you can think of them as intersections, and we have faces. So if you have a query point, uh, point where you are, your current coordinates, then you can be either on a face, in a face, so you can think about an open square. You can be on the road, you can be on an edge, or you can be on an intersection where your query point corresponds to a vertex. So this is the mathematical formulation of the point location problem, where we are interested in finding efficient algorithms, efficient solutions in terms of the size of the input. It's going to take a longer time when we have many, many more edges, but we hope that it is linear or quasi-linear n log n in the number of edges in the subdivision. So the number of roads that we consider on our map. We have seen that last time this translates into a data structure problem. So we can solve this question efficiently via a trapezoidal map. So here is another example. The example on the previous slide is actually not in general position. We have a vertical edge. We have a road that goes straight from south to north. So of course we cannot exclude this, and that will be the topic of the next lecture. But here in the trapezoidal map, what we do is we build a bounding box around it. So this is this rectangle with these four outmost green vertices. Then for every edge, we consider extensions for every endpoint. It is important that our vertical extensions do not go all the way. They can, if there is nothing there, you can have the leftmost and the rightmost vertex. But you can see that the faces in this subdivision, in this decomposition, in this trapezoidal map, are actually trapezoids. Some of them are in particular triangles, but many of them and most of them are either rectangles. The rectangles are specific cases of trapezoids. So this slide is also copied from the previous lecture. There is a double loop, but remember that for every edge you have only two endpoints. So the construction of the vertical extension is linear in the number of edges, and that was that n number. Okay, so we pre-sort our coordinates, all our coordinates of the vertex points in the subdivision on the x-coordinates. And that can already be used when we have our query point. We kind of know which vertices are involved. But actually, in order to do our queries, we actually need to also have an additional test on the height, or if you think about maps, whether you are north or south. Left and right are translated by west or east. But in geometry, we will consistently use the term left or right because we look at pictures all the time, and above and below. So in some sense, we introduced KD trees as two-dimensional geometrical data structures, generalizing the binary search trees on one-dimensional data. This is another geometrical two-dimensional data structure. So for the trapezoidal map shown here with only one line segment, we have a corresponding directed acyclic graph. So we first check on the left point P1 whether it is at the left or at the right. So if we go to the left child, we are in the region A. If we go to the right child, we check on the x-coordinate again using the second endpoint of now the rightmost endpoint of the line segment. And if we are at the right of that rightmost, then we are in region D. Otherwise, we are having to check whether we are above or below the line segment. If we are below the line segment, we go to the left child, otherwise we go to the right child. So we have two types of nodes. So this is two-dimensional. We have X nodes and Y nodes. X nodes compare to the X coordinate of the query point, and the Y nodes compare for the height above or below. So it's important that we first do the X nodes before the Y nodes. You could say it's simply convention X before Y. No, no, no. I mean, when we get to test on the segments are not lines. In some sense, you could solve this question with a test on a line, but in order for this test to make sense, you have to make sure that you really are within the segment in which, in the sector in which the line segment lies. So there is a slab. So these vertical extensions define slabs. Okay, so there is an exercise here. So the X node test is also a very simple test, just to check on the X coordinate. You only need one number. For the Y test, the Y node test, you will have to figure out how will you do this in practice. It is a primitive in the sense that it requires a constant number of operations to do. So here is the hint. I mentioned a line. You construct the line through this line segment, the 2 points P and Q. That gives you then the line represented in the format A times X plus B times Y equals C. Very convenient. Also, we have excluded vertical lines that could help you. So if A times X plus B times Y plus C equals 0, you're on the line. But then you have the inequality less than or equal. So at the Y node, you store extra coefficients that are pre-computed. So here in the X, Y, the ABC representation of a line, you store these three numbers. So you also need the X coordinate, as you can see, to do the Y test. Okay, how are trapezoidal maps constructed? Well, the title is incremental. So we are going to add one line segment. So here a second line segment is added. And the second line segment, as you could see, intersects essentially almost all trapezoids. So only C is untouched, and D as well. So C and D remain. But we intersect A and B. So the update will lead to new trapezoids. So we will replace the existing leaves, so the trapezoids are leaves in the data structure, we will replace them by the new trapezoids. But first I should focus on the update of the trapezoidal map. So how do you do this? Well, you check with the endpoints. You first check with the left point to which trapezoid does this belong. So here we find that P2 lies in the trapezoid A. And then we go to the right neighbors. So we construct a vertical extension. So this actually gives us already the new trapezoid A1. And then we go to the right. So we are still in the A, and then we compute the A2 and we compute the trapezoid E. We compute in the sense that we will remember how to store trapezoids. So trapezoids are stored, so they are computed. They are computed as being defined by 4 data elements: the left point, the right point, the upper edge and the lower edge. So if you focus on the A2 here, it has a left point P2, a right point P1, upper edge S2, and the lower edge is the bottom edge of the bounding box. So this is what it means by updating the trapezoidal map. You replace A by A1 and A2. They are adjacent to each other. So also the update is done with the adjacency information. The data structures are fitted in this way. Observe that the vertical extension that originally went to P1 actually now is shortened. So you should not have an E1 and an E2. If you leave the vertical extension all the way through P1 from the lower bottom to the upper top, the top of the bounding box, you would think that there is an E1 and an E2. Not the case. Okay. So that's the first update, the update of the map. Then we have the corresponding data structure, the directed acyclic graph that gets updated. I will do this in 2 steps. So we first focus on the A. So in some sense this slide is kind of inconsistent because the directed acyclic data structure is not correct for the right child. But let's focus on the left child. So the left child was previously entirely occupied by A. Now A is replaced by A1, A2, and E. So you see that the new leaves at the left of P1 are A1, A2, and E. So you can read this directed acyclic graph also as A2 lies to the left of P1, so it lies to the right of P2, and it lies below the segment S2. So the reading of this information is also how you navigate in this directed acyclic graph from the root of the tree to the bottom of the tree. So you can kind of see where is the Q2 here. Well, the Q2 is actually not relevant in this replacement of A by A1, A2, and E. So because you're only concerned with the region A and the what is above the um, new segment S2. Okay, the second step in the update, we go from left to right. So we now have the B that will be replaced by B1, B2, and E by those three trapezoids. So here it is. Notice that it's much more complicated, but I hope it's not that much complicated. So what do we have? So previously we had B that was sitting as the left child of the horizontal Y node at S1. So that gets replaced. So we are first testing on the x coordinate here. So Q2 is very relevant. If we are at the right of Q2, then we have our new trapezoid B2. B2 that has the left point Q2, the right point Q1, has the lower edge S1 and the upper edge is the upper edge of the bounding box. So this is how B2 is computed, was computed. So then we are now sure that we are at the right of P1 because we are in the right child of P1, but we are at the left of Q2. So the Y test on the height, comparing its relative position with the new line segment makes sense. So we are actually over here. So, and we have to decide whether we are below, if we are below, we are at B1, or we are above, then we are at E. So every trapezoid is stored only once. This is why I have this crooked arrow here. It goes all the way back to this E. But it is acyclic, so it's actually not really a tree anymore. So that's we talk about a directed acyclic graph. So there is only one direction. You cannot go back. You go from the root to the leaves. So this is a definition of the directed acyclic graph, and I should say that for every trapezoidal map, there can be a different directed acyclic graph. So it's probably now, I forgot to make this exercise, but this would be now another exercise where you swap the order. You first do S2, what is here S2, you first do that and then you do the first segment S1. So you will have another directed acyclic graph. But it will be essentially the same trapezoidal map, but with two different directed acyclic graphs. Essentially, you can have n factorial differently many directed acyclic graphs. If you have n segments, there are n factorial many ways how to order them. So there is the directed acyclic graph with the chosen order. So the data structure is unique when you fix the order of the line segments. Okay, what is now the algorithm that we are going to consider? We have a subdivision with n line segments. So the line segments are ordered. N is their number. We're going to construct a list of trapezoid and we're going to construct a directed acyclic graph. Our input is bounded, so we have built a big bounding box around this. We have these vertices of the bounding boxes. The subdivision does not contain any vertical line segments, and we want that every trapezoid has at most 4 neighbors. So for that to happen, you cannot have that there are 2 points with the same x coordinates. We have addressed this problem last time, and we will come back to a technique to avoid avoid with the assumption on the general position. So every trapezoid is therefore represented by the left and the right vertex. So this is the left P, the right P. There is the top and there is the bottom. So these are these two edges. Also, we have discussed this in detail in the previous lecture. So why is that a trapezoidal map? Because of the shape of the general shape of the faces in the map. Okay, here is another exercise. So why does the order matter? I should also probably point out, if you look to this example here, we see that A2 has actually only one neighbor. A1 has an upper neighbor and a lower neighbor. What happens if you have only one neighbor in your data structure? Well, you could have that both the upper left and the lower left are actually the same trapezoid. So you could fix it that way. So we store trapezoids. For every trapezoid, we have the address. So we actually work with pointers when we deal with left and right. So this is for the programmers amongst us. This exercise 2 asks you to describe when the depth of the directed acyclic graph is linear in the line segments. So here you can see that this is already a little bit unfortunate, but it's not. So if you work with examples 3 or 4, you can figure out what the unfortunate order will be. And I can tell you immediately what is the solution to the exercise. If you have a sequence of line segments where you intersect always and only the last line segment, the last trapezoids that you added. So remember the algorithm to build the search data structure replaces the leaves. If you start replacing here and there, and then your tree will remain balanced. But what if you replace always the same leaf? And that corresponds by taking an order or by taking a configuration why when the last line segment lies always in the last used, the last added trapezoids. The trapezoids that then also is deepest in the tree. Okay, so that's the problem. So let's solve the problem. So here is the algorithm again. So so we start with the problem specification, the input and the output. Why is again the randomization is going to help us? Well, if you think about the solution to the previous exercise, you need to be extremely unlucky to always pick the next segment, one that will change one of the trapezoids. So there are n factorial many orders. N factorial grows extremely fast. So the idea is that on average, over all possible n factorial orders, it's extremely unlikely that you're going to have such a very unfortunate outcome. So that's the idea why a randomized algorithm will actually help us out. We will make it more formal. We will prove this in the next lecture. So the algorithm will, for every new line segment, so that is the main loop, it will locate the trapezoids. And here you can see the n log n coming in the time. So the main loop runs over all the line segments. We have n of them. And the step one, the location, is actually a binary search. And if the tree is balanced, that will be logarithmic in the number of line segments. So we have the n log n time. That's kind of natural out of there. Okay. Um, this is the high-level overview in pseudocode. So again, start always with the input-output specification. That fixes the notation again. So we start by constructing a bounding box. That can be done typically by selecting also the left and the rightmost vertex, the upper and the bottommost vertex. That's the initialization for our trapezoidal map. So that is S0. We have the vertices, the 4 vertices that will be used. So this will be testing on the X and the Y coordinates, whether we are at the left, where we're in the box or not. Then we have the permutation. So an alternative algorithm would pick in the main loop each time in the next vertex. But we have seen, and that was an exercise when we first encountered randomized algorithms with randomized incremental linear programming, that there is a linear time algorithm to execute step 3. Okay, so before we start the loop, we have actually already done n steps by executing permute. Also, in some sense, looking for the bounding box, we had to compute the minimum and the maximum. So that is also already one complete scan through all the line segments. Okay. Then comes the main loop. 3 steps in the main loop, steps 5, 6, and 7. We will locate all the trapezoids that are intersected by the new line segment. So the follow segment takes on input the current trapezoidal map that we have, the current directed acyclic graph, and the new line segment, and it returns a sequence. So here there are k plus 1 many. It returns a sequence of trapezoids. We will see it's actually can be looking quite complicated, but if the k equals 0, there's only one delta 0. So that's actually the case that we could look at it first, when there is only one trapezoid affected. Okay, so then there are the routines 5 and 6. So we have to update the trapezoidal map, replacing all the affected trapezoids by the new trapezoids. So we start with K, we have L. So K and L, they are typically different numbers. And then we also update the directed acyclic graph, replacing the leaves in that tree, so the delta 0 up to delta k, with the new leaves, using also the new line segment. Okay, why is this algorithm going to work? Well, we will, in some sense, in a proof of correctness, we will work with a proof by induction. We assume that we have a correct trapezoidal map for the current I segments. So I runs from 1 to n. So for the previous I minus 1 segments, it was correct. We're going to show that by updating replacing the trapezoids at the leaves in the map and in the directed acyclic graph, we will actually still get a valid search structure. Um, Actually, it will turn out that these correctness proofs will be made as we are constructing the algorithms. Okay, how do we locate intersected trapezoids? Well, it may be first good to look into an example. And it's also an exercise. In some sense, I delivered this lecture here. I'm already half hour in. So this is done in one sitting, but the exercises actually invite you to pause a little bit and here reflect back on what this directed acyclic graph actually is. So there is choice here. So you see 4 given line segments. So the SI is actually not really in the picture. So this SI will be used in the next lecture and in the next slide. So there is choice depending on which order you picked in the segment. So you will have to order the line segments. So the I is actually here in this case 5. Depending on how you order the line segments, you will have a different directed acyclic graph. Okay. What's the algorithm now to locate the intersections? And perhaps I can probably represent this better by looking at side by sides. So this works here. So what do? We have our new segment SI. So the exercises 3 and 4 are kind of linked. So studying this picture here, we have left endpoint, and we're going to search in the directed acyclic graph for the trapezoid to which this left point P belongs. And you can see, and that's the first step, so that is logarithmic in the height of the directed cyclic graph. We assume here that it is logarithmic in n now because we had a lucky order. We don't have an unfortunate order. You can see that in the remainder of the algorithm, the P no longer occurs. We will exploit the fact that we can always go to the right neighbor. So we will navigate to the right of the line segment. So we will navigate to the right. We will keep on doing this. So every trapezoid has a right point. So if we go to the neighbor of delta 1, we see that the right point here is at the left of Q. Q is the right point of the new line segment, or phrased equivalently, the right endpoint of the new line segment is at the right of the right point of the current trapezoid. Okay, so that means that if we are actually at delta 0, so I went perhaps a little bit fast to look at delta 1 already. If we are at delta 0, we have this uppermost right point, which is to the left of Q, or Q is to the right of it. So we need to go to the right neighbor. Here, the algorithm, you may have to check whether you are above or below for the lower or the upper neighbor, but there's only one neighbor to delta 1, so you could resolve this dilemma. There is no lower or right. Say that both the lower and the right, it's actually the same trapezoid. So the right point is above, so we get then the lower right. So it matters with delta 1. If you look at delta 1 has actually an upper and a lower neighbor. So the lower neighbor is actually the one we need to consider. And you see that indeed the test 3 is correct. The right point of delta 1, so that is that very tiny segment here, that is actually above SI. So that's why we then pick the lower one. So I didn't name the trapezoid that is above the short statement. Okay, so I have kind of solved exercise 4 by talking. So exercise 4, if you have to hand this in, you can actually do this. I said that exercise 3 is kind of a prerequisite, but then also not. So you can, um, exercise 3 kind of slows you down a little bit, allows you to think about, requires you to think about the search structure. So there is no formal proof of correctness. So this would be an extra exercise, but there are already many exercises in this lecture. So for if you want to have a proof of correctness, you have to prove two things. You're not going to forget any trapezoids, and you're not going to report any superfluous trapezoids. So if you would forget trapezoids, then you would not update. So trapezoids that need to be adjusted and replaced would not be. If you would report too many, that might also lead to problems. So there are two statements that you would need to show for the correctness. And it's a proof by induction. So it actually relies on the fact that the directed acyclic graph is actually going to give you the correct answer for the delta 0. So delta 0 is based on that induction hypothesis. All right, so let me go back to the original format here. So it is an exercise to show that I don't know if there's something wrong with my eyes, but this is all very blurry. Now if I do this, let me refresh my screen. So there it is. So the correctness is here. It brought me to the right spot. So the correctness of follow segments requires some statements, which we are not doing here. Okay, so what are now the algorithms to update? So there are two cases. So one simple case is you need to replace only one trapezoid. So what happens is that then if you look at the trapezoidal map first, you add the extra vertical extensions. You compute the A, B, C, D. So A lies to the left of the left endpoint of the new segment. That left of the new segment is the right vertex of A. The left vertex remains the left vertex of the original trapezoid. And now you see why this is actually simpler. I mean, we have already the top and the bottom of the original trapezoid. So updating the trapezoidal map consists in computing the all the information that you would need to represent every trapezoid. For the directed acyclic graph, you first compute the x nodes, here represented by pi and qi. So you're first going to check for any point, does it lie to the left? Then it lies in the trapezoid A, or does it lie to the right? So then we are going to compare with the right endpoint represented by QI here. And only then, when we are sure that we are in the proper range for the above and below test to make sense, then we have the new um, node, the new Y node. So one of the exercises will be to write pseudocode. I'm actually here telling all the steps that need to be done. So in some sense, this is also a constant operation. So you can see that you can have always 4 new trapezoids. This update. All right. So write your answer as a function in pseudocode. So in some sense, I should have scrolled further. But you see, this slide is more precise in the sense that the picture has the correct labels for the 4 data attributes for the trapezoid that will be replaced. So for each new trapezoid, you have to define what are these 4 data attributes. So what is top of A, bottom of A, left point of A, right point of A. So this will be 16 statements that you have to write. Here we have then the more complicated case where a line segment intersects several trapezoids. So what you then do is that, so these trapezoids delta 0, delta 1, delta 2, delta 3 were given to us as the output. So we have for every trapezoid the extensions, the right point. So we can define using these, each time we actually use the right of the until the next to last. So, and we define the vertical extensions using the right point of the trapezoids here in the example 0, 1, and 2. For 3, it's no longer. Well, for 3, it's actually also necessary. Then you use the right each time. So you may have to shorten so that the end at the new segment. So that's the key property of a trapezoidal map. And then we can identify, so we also can compute the A, B, C, D, E, and F here in this example. It's also good, I don't know if this is an exercise. No, it's not. So we actually have, so the exercise 5 is actually doing the specific case when there's only one trapezoid. So what this exercise asks for is pseudocode. And the first initial reflection is to go to the textbook. The textbook has another narrative or very similar narrative, but also the textbook actually does not completely specify in great detail all the steps here. It explains this via examples. So exercise 6 is intended to be more formal. Exercise 6 would also be necessary if you're going to go for a formal correctness proof. How is the search structure updated? And this is almost my last slide. So we will replace the leaves. And in some sense, it looks at first complicated, but now notice that the tests that you will be using will not be using pi, because we know already that we are at the right of py. And we will use the last endpoint only with the last trapezoid that gets replaced. So in some sense, this is shown for 4 trapezoids, but you can see the structure of the tests that are being added. We are adding Y nodes except for the very last trapezoids. That's why essentially the we have a special case in case there's only one trapezoid that needs to be replaced. Then actually there's only one above and below test with that needs to be done. Also, you need to take into account then the P and the Q. Okay, so yes, in some sense, it's not completely general. What if PI would not be a vertex here? So in some sense here, I have the special case where we have already a vertex added. So you would use PI in case PI would be not already be a vertex. But then, so here we have this special case where a trapezoid has a left point where both top and bottom meet. We are storing every trapezoid only once, and that is reflected here in this picture. Okay, I'm nearing the end of my allotted time. Write pseudocode. Again, some of the cases, one of the cases has already been done. So if you looked at the case for the first case when there's only one trapezoid that is affected, and you already get half of the credit by very in great detail make the input-output specification. This exercise is necessary in a formal proof of correctness. Okay, what is then actually the main result? We will prove this. But you can already see that the randomized algorithm will kind of exclude the very bad cases, which are very particular and which are very rare compared to all n factorial possible search trees that you can get. You get the n log n factor because there is the n from the pre-processing already when you compute a random permutation. But there's also the n because you're adding one step at a time. You add the segments. The log of n is by the depth of the search structure. The size of the search structure is also linear now in the number of line segments. And as a consequence, in some sense, the third statement is a consequence. So if you have a search tree that is logarithmic in depth, then indeed, for every query point, the query time is logarithmic. So I'm almost done. We will prove this theorem and actually also remove the general position assumption in the next lecture. Okay, what have we done? Trapezoidal maps and their corresponding directed acyclic graph. So if there is a directed acyclic graph, it's the graph if you fix the order of the line segments. So we have a very nice solution of the point location problem, which kind of explains why smartphones can solve your point location very quickly and help you navigate. There are many exercises in this lecture, but they are mainly meant for you to pause a little bit and reflect on the new data structures and the new concepts that we have considered. Also consider the exercises in the textbook. And last time we looked at Seagal, we can look at it again, but I will not do this because I'm running out of time.